You can view the animation for stress by selecting stress and right-click to select animate.
Hello everyone! Once again, Soriddowākusu is here. For today's video, we are going to analyze the stress and deformation after applying the simulation to the material, which is an I-beam that we are going to create using SolidWorks. Before we start, please support our channel by clicking the subscribe and notification bell button. Click the like button if you like this video. Let's begin. We will start on creating the I-beam. Upon opening SolidWorks, create new part document and select the right side as the base. Click the rectangle command on the upper left part to create random quadrilateral. Modify this figure into 100 by 60 mm using Smart Dimension. Create a vertical line on the center. Then click Trim Entities above to remove the lines in the left and right side. Using Offset Entities, offset internally the upper and lower lines by 5 mm. Using the same command, offset the vertical line twice into both opposite sides by 2.5 mm. And delete the central vertical line. Make vertical lines that will serve as the side corners of the upper and lower horizontal parallel lines. Click the Trim Entities to remove the unnecessary lines. On the upper part, click the Fillet command. Fillet the sides of the inner part corners of the upper and lower side of the beam by 4.9 mm. Go to Features toolbar and click Extruded Boss Base and extrude the beam by 3.65 meters. We have now created our I-beam that will use for simulation. You can view the different views by clicking the multi-view so that you can also check your figure. Next up, the simulation processes.
After creating the I-beam, we will now apply simulation into it in order to analyze the stress and deformation. Make sure that you already had the SolidWorks simulation on the software. After clicking SolidWorks simulation, on Add-ins toolbar, click the new study under Study Advisor above, then click Check to begin. Click the Apply Material to apply the desired material for the beam. We have selected AISI 1035. The Fixture Advisor located above can make the beam to be fixed on location, depending on your desired part. we have selected fixed geometry under this command and applied it on the face of the right side and left side. Click Force under External Load Advisor above to apply the force on your desired location. We applied 14,500 on the middle front face. After assigning desired fixtures and loads, you can click Run this study above to show the stress and deformation. You can view the animation for stress by selecting stress and right-click to select animate on options. You can also view the animation for strain by doing the same thing. That's for the simulation of our I-beam. Let's now proceed to analyze the stress and deformation. We will also explain the theoretical method and explain the comparison between the theoretical and the SolidWorks computation.
Based on observation, the area in where a force of 14.5 kN applied on the beam resulted on blue. As per indicated on the bone Mason scale, this color is located on or less than 4.489 times 104 Newton per meter squared. In addition to that, the beam bended after the given force was applied. On the other hand, according to the computation of the software, the form stress on some plunge part of the beam, especially on the part near the fixed area and the middle area of the plunge, is greater than the stress on the area where we applied the force. In fact, there are some areas indicated from yellow-green to red. Considering that the ultimate stress or ultimate yield strength of this material, AISI 1035, which is equivalent to 2.827 times 10 raised to 8 Newton per meter squared. Those part which is above the yield strength might deform permanently because permanent deformation occurs when the form stress is higher than the yield strength of the material. The plunge shows greater stress than the other part of the beam. It simply indicates that this part needs to be improved and have a stronger support to withstand the stress caused by 14.5 kN force.
Taking a quick peek on displacement results, we can observe that the middle part has the greatest displacement along the beam, in which it reaches 5.50 mm or above. The result is reasonable since the applied fixtures on both ends have a greater impact on the nearest location of the beam. The nearer the location of the beam parts from the fixture, the lower the displacement value because the fixture will support the beam to be fixed on the designated location. As for the strain and deformation, we could observe that the deformation happened on the area where we applied 14.5 kN force, drops from 3.527 times 10 raised to negative 7 or below. This is indicated as for the color slightly darker blue located on the strain scale. Moreover, we can observe from the result, the strain on some parts of the flanges are greater than the area where we applied force, especially on the part near the fixture and on the middle part. There are also some parts on the corner, on the attained red color, which means it has the greatest strain along the beam. The numerical value that falls from 2.832 times 10 raised to negative 3 and above. The factor of safety that was calculated on the simulation is 0.33, and as you can observe on the beam, it resulted on red, which means that it lies down on 0.33 or below. This factor of safety is calculated by getting the ratio of allowable stress to the actual stress. The factor of safety less than 1 represents likely failure. Therefore, the beam is subjected to fail after applying 14.5 kN.
For theoretical analysis, we will going to find the stress and the strain by using Young modulus of the model given. First, we will solve the stress, and for that, The formula of stress is the force applied over the area of the model. In order to find the stress, we will use the given of 14,500 Newton of force, a length of 3.65 meters, and a width of 90 millimeters. To find the area of the model, we must multiply the length and the width of the model, which will give us the answer of 0.3285 meters squared. Now that we have the area, we must divide the force, which will be 14,500 Newton or 14.5 kilonewton over the area, which is 0.3 meters squared. This shall give us the stress of 44,140.03 newtons meter squared or 44.14 kilonewton over meter squared. Having a Young modulus given by AISI 1035, which is 2.05 times 10 raised to 11 Newton meter squared, we have the ability to find the strain of the object. Strain's equation can be stated as stress over the Young modulus. Therefore, strain is equal to 44.14 kilonewton per meter squared of stress over the Young modulus, which is 2.05 times 10 raised to 11 Newton meter squared. This should give us the answer that the strain is equals to 2.15 times 10 raised to negative 7.
Our comparison on the computation of stress and strain using SolidWorks and using theoretical on our solution or solving, which means calculating using theories and formulas. There are the two images about stress comparison with the use of SolidWorks and theoretical solution. After we calculate the stress using theoretical, we got an answer of 44.140 kilopascal, and when we compare it to the scale of bone misses that has a scale of 44.89 kilopascal to 285.6 megapascal, and our answer is located at the bottom of the lowest scale, but with the force of 14.5 kilonewton, the beam started to bend at the middle area. By analyzing the data, this means that the two coincides with each other. Based on the computation of strain using theoretical and SolidWorks simulation, the lowest strain that you can see is located at the scale with dark blue in color, and the highest strain is the red color. Using the theoretical calculation, we got an answer of 2.5 times 10 raised to negative 7 for the strain, which is below than scale and has a color of dark blue compared to the other part, like flanges and the fixture, where it has higher strain that ranges from 7.082 times 10 raised to negative 4 to 2.832 times 10 raised to negative 3. As we observe the simulation, we can interpret that the area where most are blue can hold the given force, and the red color interprets that it has the highest strain of all. We therefore conclude that factors may have effect on the stress-strain properties of a materials, such as the types of material used, the location of the fixture, the load or force that is applied to the material, and the direction of the force on the material.
Thank you so much for watching. It is a pleasure for us that you have watched this video, and we hope that you have learned something from this content. Again, if you like this video, just click like, and please don't forget to subscribe to our channel. You may click the notification bell if you want to be notified by our latest content. That's all from this video, and goodbye. Bye-bye.